Hello everyone, my name is Dylan and I'm back again with another walkthrough of the 2024 SATs papers. This is the second paper in the maths set. There are 3 in total. We've already gone through the arithmetic. If you're watching this very quickly after it's released, we haven't done the next paper yet, but more than likely we have. So go to our channel and you'll see paper 3 as well, which is the other reasoning paper. But this is paper 2 reasoning. And before I get started, as I'm scrolling, I'm going to talk to you about the reaction to this paper. Now, a lot of teachers were talking about it and saying, my goodness me, it was tricky. It was a very difficult paper in terms of there was just lots you had to do in a lot of questions just to get 1 or 2 marks. So you'll see what I mean as we go through this. But we're going to start with question 1. Here is a triangle on the grid. Draw the reflection in the mirror line. We did a lot of practice on this on our YouTube channel beforehand. So if you watched it, I'm sure you would be able to get this question right. What we need to do is take a corner of the shape and count how many squares to the mirror line. There's 2. So we keep going 2 more. And that corner now is over to this side in a reflection. Let's take the corner at the top here of the triangle. 1, 2, 3, 4 away from the mirror line. 1, 2, 3, 4 away from the mirror line. So we put it over there. And this one is 1, 2, 3, 4, 5 away from the mirror line. 1, 2, 3, 4, 5 away from the mirror line. The only thing I would say to you here is use a ruler. Don't do what I'm about to do because it says use a ruler. I'm using freehand with my mouse. And we can go across and along. And that's the reflection. What they'll be looking for is you've used a ruler for the lines and the corners are in the right coordinates there. So that's how we reflect. Quite a straightforward start. Question 2. This table shows the cost of fruit at a school cafeteria. Blah, 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 blah. Amir buys 2 pieces of fruit. He pays with a £2 coin and he gets £1.50 change. That's going to be important information in a minute. Tick the 2 pieces of fruit that Amir buys. Well, we don't know yet until we actually figure out how much the 2 pieces of fruit cost Amir. And we can do that simply by finding the difference between £2 and £1.50. So if you pay £2 and get £1.50 back, that means you spent 50p. That's the first step to this question. Next step is then to think, okay, which 2 pieces of fruit add up to 50 pence? We can use trial and improvement here, however you want to go about it. But the 2 amounts that add up to 50p are the pear, which is 38, and the banana, which is 12. So you should tick banana and pear. That gives you 50 pence in total. Next up, question 3. Layla plays basketball. This graph shows how many points she scored in her first 3 games. Number of points going up the y-axis and the game on the x-axis. After 4 games, Layla scored a total of 25 points. Complete the graph and use a ruler. So what it's asking you here is how many points did Layla score in the 4th game? Very common SATs question where you're given a number of parts, you're given the whole amount, but there's 1 part missing. So the first thing you should do here is label how many points she scored in each game. We can see here game 1 is 7, between 6 and 8. Game 2 is between 4 and 6, which would mean 5 points. Game 3 is nicely on the 10 line. So far we find the total 7 plus 5 plus 10. That gives us 22. And we know that she scored 25 in total. So how much do we have to add on during game 4 to end up at 25 points? That's the first part of this question. Well, hopefully that's quite straightforward. It's 3. But the question wants you to complete the graph. It doesn't want you to write down 3. If you wrote this down, you're just setting yourself up to get the answer marked incorrectly by the marker. We want it to be 3 as the answer. So we go over to our y-axis between 2 and 4. So we're going to draw a very straight line here. Remember, you would be using a ruler. Go straight down, and that would be it. You don't have to color it in, you have to label it. You just simply complete the graph as long as it's showing 3, somewhere in between 2 and 4, well, halfway, exactly. Question 4. The numbers in this sequence increase by the same amount each time. Write the missing numbers. So as soon as we see a sequence where the numbers are increasing by the same amount, this is called a linear sequence. And what we need to do is try and find 2 numbers next to each other. So we do have that here in the middle, luckily for us. So how do we go from 1 to 7? Well, we add on 6. So now we figured out what's happening each time. It increases by 6 every time it jumps. So this one here is very simple. 7 plus 6 going to give me 13. You can check it because you can add 6 again. And yes, you get to 19. So that's cool. But this is only 1 mark. So we wouldn't get anything if we just finished there. We need to also figure out what's in this box. 2 ways to do it. Add 6 on to minus 11. Now, you may get trapped there and write down minus 17 because you're thinking, well, 11 plus 6 is 17. If you're adding a negative number, it's going to get closer to 0. So it's the same as thinking of 11 take away 6. That would get us to minus 5. Of course, we all know minus 5, negative 5 is bigger than negative 11. That's because when we go into negative numbers, it flips. We could again check this by doing 1 take away 6. We could use the inverse. We'd end up at minus 5 either way. Question 5, write them 3 missing digits to make the multiplication correct. This is a really interesting question because there's always going to be some kind of exchanging going on. That's very often what happens with these missing digits. We think, well, there's going to be some exchanging because straight away, something multiplied by 3, so something in the 3 times table, ending in a 2. Well, that's the point. It has to end in a 2 because something times 3 can't be 2. Doesn't make any sense. So what multiples of 3 end in 2? Well, we have 12. 15, 18, 21, 20, 24, 27, 30, 33. I mean, we have to go all the way up to 42 after that. So 42, that would be a much bigger than a 1-digit number. So the only 1-digit number we can multiply by 3 to get an answer that ends in 2 is a 4. But this is the important part. 4 times 3 is not 2. It's 12. So we have to put a 1 down here. Now, luckily for us, we actually get the digits we need. 5 times 3. Well, I know that's 15. But you've got this 1 to contend with. So it's actually 16. Cross out that 1 because we've added it on. 3 times what equals 7? That's impossible. No, it's not, because look, it's this exchanging again. What we actually want is to have an answer that's 6, so that when I add on this 1, it becomes 7. So 2 times 3 is 6, plus this 1 we've exchanged makes 7. Without this idea of exchanging and knowing that you've got to do this, this question is impossible and really tricky. Okay, so you can check that it's right because now you've written this out. You could literally just do 254 times 3 and see if you get 762. You will. Question 6. Olivia's thinking of a number. My number is greater than 236. Okay, so 236 on a number line has to be bigger than that. But it's less than 245. So the longest end up here is 245. Has to be something in the middle. It has a 3 in the tens place. Okay, so 240, it can't be. So it has to be something in between these numbers now. So it's either 237, 238, 239. It's only those ones. It has a 3 in the tens place. We've done that. It has an even number. Aha, so it can't be 237. And it can't be 239. So we've narrowed this down massively now. There's only one number in between this. It must be 238. Question 7. A box holds 40 packets of envelopes, and each packet holds 25 envelopes. Do you say envelopes or envelopes? Let me know in the comments down below. So, how many envelopes does the box hold in total? This is a simple case of 40 packets multiplied by 25. Something I'm just going to say kind of out the blue here. This is a very common jigsaw arrangement. You have 40 across and 25 down because that's for a 1,000-piece jigsaw. So it is 1,000. Again, if you wanted a cool way to work this out, a really interesting thing when you multiply two numbers together is if you double one number, so this becomes 50, and if you half the other number, so this becomes 20, the answer is exactly the same. So let's do it again. Let's double 50. We end up with 100. And let's half 20. We end up with 10. All of these three give you the same answer, but one is much more easy to work out in my opinion, which is the bottom one. So this is 1,000. And that means that the others are 1,000 as well. You can prove this. Let's just pick 8 times, I don't know, let's say 24. Yeah, 8 times 24. That's the same as 4 times 48, which is the same as 2 times 96. And you might be much better at doubling. So instead of doing 8 times 24, you might prefer to do this. Gives you the same answer. So the answer there is 1,025 multiplied by 40. Write a whole number in each box to make these statements correct. This question. It's a cool question, but it's just another example of how this paper 2 was made trickier. Lots of children are used to just working out, given a number, round it to 10. Give it a number, round it to 100. Give it the same number again, round it to 1,000. They had to just go one step further here and just test you guys really, really, really trickily, in my opinion. So write a whole number to make the statements correct. One's been done for you. 18 rounded to the nearest 10 is 20. Now, this is something where there's actually lots of different answers. You could have put 17 in here. You could have put 21. You could have put 22. Lots of different answers. Rounded to the nearest 1,000 is 4,000. So anything from 3,500, that would count. And you could go all the way up to 4,499. Any number in between those two would count. That's a huge range. But the point is, when you round it to the nearest 1,000, anything in between here is closer to 4,000 than 3,000 or 5,000. Again, round it to the nearest 10,000. The lowest number you could have put is 815,000, because at this point you would round up to 820,000. The highest number you could have put is 824,999. Because anything more than that, you'd then have to round up to 830,000. So there's the range. I can't give you an exact answer here, but if your number was between this range, you would have got the mark. But look, 1 mark. 1 mark. You have to get both. Even if you do fantastic maths here and just get a bit stuck, you don't get rewarded for doing this maths unless you do all of it. I think that's a bit harsh, I must say. Question 9. 2 of these calculations have the same answer. Write the answer as a decimal. So let's just work it out. It's always the best thing to do here. 4 divided by 10 is 0.4. Shift the digit down 1 place. 4 divided by 100. Well, straight away I know these are different because we start at the same number but do something different to it. 4 divided by 100 is 0.04. Excuse my writing. 40 divided by 10, that's 4. So all 3 of these different so far. What about this last one? 40 divided by 100, shift it down 2 places, we get 0.4. So these 2 have the same answer. Luckily for us, we've already done the hard work of writing as a decimal because that's how we figured it out. 0.4 is the answer. Question 10. Circle the 2 prime numbers that have a difference of 2. A prime number is any number with only, well, exactly 2 factors, itself and 1. So let's get rid of any other numbers which have factors other than 1 and itself. 15 is not prime because it goes in the 3 times table and the 5 times table. 17 is, because it's not in any other times tables. Neither is 19. However, 21 is in the 3 and the 7 times table. 25 is in the 5 times table. Okay, so we're left with these 3 prime numbers. But the question says circle the 2 prime numbers. Why 2? Well, they have to have a difference of 2, which is 17 and 19. 23 is too far away. Question 11. This table shows the number of children and adults at a childcare centre. Complete the table to make it correct. The first row has been done for you. This is so convoluted and confusing for what is basically just a times table question. Let me show you what I mean. 1 and under. Number of children, 12. The number of adults is 4. So the number of children per adult is 3. That means that for every adult, 1 adult, there are 3 children. It's kind of like a ratio question, but really it's just a multiplication question because all we have to do is take the number of adults and multiply it by the number of children per adult, and we end up with the answer at the other end, which is 12. So 4 times 3 is 12. Number of children per adult is 4. Well, if there are 20 children, we have to do 20 divided by 4. There must have been 5 adults. We can check again because for every adult, there are 4 children. 5 times 4 is 20, and it works. 3 adults, for every adult there are 8 children, so we do 3 times 8 and we end up with 24. Okay, simple as that. This is literally just, all this question asked you to do here was 20 divided by 4 and 8 times 3. Incredibly easy maths, but what a, some might say nasty, someone might say genius way of putting it into a problem to show problem solving skills. Question 12. Shapes W, X, Y, and Z cover different fractions of this 10 by 10 square. This is vital information because what this tells us is there are 100 pieces, and you'll see why that's important now. Match each shape to the correct fraction. So, what coverage is there in terms of a fraction? Well, straight away, I can see here 1 out of 100. Well, that's simple because there's only one shape here, which out of 100 blocks is taking up just one space, and that's Y. So I know shape Y is 1 out of 100. Now what's interesting is the rest of them aren't out of 100 because what we're going to have to do is figure out what the fraction is out of 100 and then do equivalent fraction working out. Another step. My goodness, they really have made this tricky, this paper. I do think paper 2 was quite hard. Let's just start with W, shall we? W is 5 across, 5 down. That's 25. 25 out of 100. Ooh, that's interesting because if I know W is 25 out of 100, I can actually simplify it, and I should know that 25, if I see that, 0.25, that's a quarter straight away. And we could simplify it because we could say divide 25 by 25, we get 1. Divide 100 by 25, we get 4. So actually, shape W is 1/4. And we can even, look, do this. If I just cut this in half, and then half again, you can see there that W is quite clearly 1/4. Let's do Z next. We have 1, 2, 3, 4, 5 across, 2 down, so that's 10. So Z is 10 out of 100. Which fraction here is the same as 10 out of 100? Well, it's just 1 out of 10. Look at that, 10 out of 100. Divide both by 10, you get 1 out of 100. So shape Z is 1 out of 10. We don't even need to work out X. It's 2/5 because it's the only one left. We could do if we wanted though. This is 40 out of 100, which simplifies to 4 out of 10. And it simplifies again to 2 out of 5. So that does work. Doesn't matter what order you do it, but if you've got only one left and you're confident with your working out, just move on. Put the answer and move on. Question 13. Match the name of each 3D shape to the number of vertices. Vertices is just a word that we use for corners in a 3D shape. And whenever I'm doing 3D shapes, I always imagine building them with marshmallows and spaghetti, because I do that sometimes with children who I'm teaching. It's a really cool way to do it, because once they build the shape, you can use the language vertices, obviously, and you should, but it's something they can grasp onto and say, well, okay, look, the vertices are just how many marshmallows we used, because they're the corners. The vertices join together the edges, which is the spaghetti. So if we're thinking about a cube has 8 vertices, 4 at the top, 4 at the bottom. And once you start visualizing it as spaghetti and marshmallows, it does actually help some children. So 8 vertices there for a cube. Square-based pyramid. So we know it's going to be a square at the bottom, and then one vertex, we would call it, at the top to join them all together. So that's a square-based pyramid right there. Again, you might be able to draw them to help you. You might not, but building it really does help. So square-based pyramid has 5 vertices. Triangular prism. Okay, I'm going to keep drawing. I'm going to have a triangle at one end, so that's 3 straight away. And the definition of a prism is simply you have the same shape at the other end. So there's 3 more. And all we do now is just join them. So there's no more vertices to draw in. 3 at one end, 3 at the other. So therefore we have 6 vertices with a triangular-based prism. And then we have an octagonal-based pyramid. What a strange thought. You may well have never come across an octagonal-based pyramid before, but hopefully it's really simple, because you know the octagon, it must have, I've never tried to draw one, by the way, it must have 8 vertices at the bottom, because the base is an octagon, and we know octagons have 8 edges and 8 corners, and then we're just going to have one marshmallow at the top. 1, 2, 3, 4, 5, 6, 8. Either way, we know it's 8 plus 1. And do you know what? Like I said before, you've only got one answer left, and you're thinking, what's an octagonal-based pyramid? I don't know. Well, you knew the other 3, so it must be 9. There's only one left. That's how you're going to get a mark there. Question 14. A class votes for a captain. 3/4 of the class vote for Sam. I'm working with quarters. I like to draw a bar model representation. Split it in half, and then split them both in half again. Now I've got quarters. 3/4 vote for Sam. So 1, 2, 3 voted for Sam. The remaining 7 pupils voted for Alex. So this remaining lot is Alex, and we know that this quarter remaining is 7. How many pupils are there in the class? This is about recognizing that if 3/4 voted for Sam, 1/4 voted for Alex, and we know that's 7. So if we know 1/4 is 7, we can fill the other quarters with 7, which means 21 voted for Sam, 7 voted for Alex. But the question says how many pupils are in the class. So 4/4, 4 times 7, there must be 28 people in that class. And this is just a really good, hopefully, proof that just drawing a model can really help you to visualize a question sometimes. Question 15, write the missing number to make this multiplication correct. This was a question type that I looked at before the SATs. If you want to go and take a look at my previous videos, which was how to very quickly answer questions without having to do lots of working out. This is an example here. We have a number times 100 is the same as a number multiplied by 10. So what we know here is that we're only multiplying by 10. This must be 10 times bigger. Whatever we start with here must be 10 times bigger of what we started with there. So we get 32.07. I've not done any working out other than if they're going to be equal, I had to multiply this side by 100, so it must be smaller. This side I only multiplied by 10, so I made what I started with 10 times bigger already. You could prove this. You could work it out that this is 320.7. And then you would work this out as 320.7. That is fine if you've got time, but if you can just notice those patterns, you're going to save time for sure. Question 16, here's a number. This, by the way, tricked a lot of people. Let's take a look. Tick the statements that are true, because it seems quite an easy question on the surface. The 5 digit represents 50,000. Well, where is the 5 digits? It's in the 10,000 column. So 5 lots of 10,000 is 50,000. That is true. The value of the digit 9 is 900,000. Where is the 9? That's in the millions column. So therefore it is worth 9 million, not 900,000. Keep this blank. It's not true. The digit 6 represents 6 millions. Well, we just spoke about how the 9 actually represents millions. The 6 is 600,000. Leave it blank. And here's the tricky part. The value of the digit 2 is 20 tens. Well, let's look at the 2. You might think, well, it says tens, 2's in the hundreds. So it's false. No. This statement is true, and here's why. 20 tens. 20 tens. What is 20 tens? Well, 2 tens would be 20, so 20 tens is 200. You can literally cross 20 tens out and write 200. So the statement is now, the value of the digit 2 is 200. That is correct. What a nasty way to check your place value. Really interesting though. Really interesting question. Chen buys these 4 items. Chen pays for the 4 items with a £10 note. The price of the butter is not shown. She receives £3.85 change. What is the price of the butter? Now, straight away, I'm going to tell you something. Look, we are given the weight of these items. This information is not relevant at all. And there was a lot of reaction to this. People saying, why would we give things we don't need to use in a question? Well, my opinion is actually it's part of the problem solving process, just to realize, okay, this is all about change and cash. The grams and the weight I'm not going to use. That's a problem solving skill, to be able to figure out, oh, I don't need to use that. So you don't need to use that at all. It's completely irrelevant. However, again, this is a really common stat style question. And if you watched any of our prep videos, we talked about it a lot. It's combining two of them, actually. One is finding change, always comes up, something to do with change. The other one is when we have parts and the whole, but one of the parts is missing. So the first job I would say in this question is to work out actually in total then, what did these 4 items cost? Because we don't know, we can't add it up, we don't have the butter. But what we can do is know that Chen, she spent £10 and she got £3.85 change. So the first thing I'd be doing is to be taking £3.85 and thinking, okay, what's the difference up to £10? Because that's how much the shopping cost. So I'd do a first jump of 15p, which would get me up to £4. And then £4 to £10 is really easy because that's just £6. So I know in total, £6.15 is what the shopping cost altogether. Okay, that's my first thing I'm going to do. Now I've kind of created my own question because I knew £6.15 is the total for all of this. And again, I'm going to draw a little bar model at the top because we've got the apples, 150. We've got the bread, and it's written down as £0.70. I'm going to keep it all as decimals, even though it's 70p. The butter we don't know. I'm going to leave that blank. But we do know the cereal is £1.45. And then I'm going to put the butter at the end because we don't know it. We just don't know this. This is what we're trying to work out. But I do know the total amount, including the butter, was £6.15. So how do I work this out now? Well, okay, what I would do is work out the apples, the bread, and the cereal, put them all together, and then take it off £6.15. So the apple, it's £1.50. The bread, 70 pence, so put 0.70. And the cereal, £1.45. Okay, that's 5 in the 1p column. 5 plus 7 is 12. Plus 4 is 16 in the 10p column. Exchange over the 1 to the pounds. 1 is £3.65. So now, to figure out how much the butter cost, we need to know the difference from going up to 365 up to the real total, which was 6.15. So to find the difference, we're going to simply subtract £3.65 from £6.15. And then we're finally at the answer. 5 take away 5 is 0. We're going to have to exchange here in the 10p column. So we have 11 10p's, take away 6 is 5 10p's, put a decimal place, 5 take away 3 is 2. And the butter costs £2.50. A very tricky question, in my opinion. Not helped by the fact that there was some added information that wasn't needed. But is it a fair problem-solving question? I don't know. Let me know in the comments what you thought about it. Question 18. Draw an arrow on the scale to show 1,350 grams. Well, the important thing here is in the question we have grams. In the actual given scale, we have kilograms. So what do we have to do? Well, I would just convert. I would write down 1,500. It's about knowing that 1 kilogram is 1,000 grams, which is an important fact to know. And this is 2,000. Now it becomes more easy for me because I prefer working with whole numbers like this than decimals when it comes to a scale. So what are we going up in? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 jumps to go from 1,000 to 1,500. So 10 jumps to add 500 grams. That means each jump is 1/10 of 500. Each jump is 50. So I'm actually going to go past and do 2 jumps is 1,100, 1,200, 1,300, and the question says 1,350. So that means that 1,350 must be right here. Each jump's 50. You could have worked backwards to 1,500, 1,450, 1,400, 1,350. Doesn't matter. The important thing here is to realize each small jump is 50 grams. That's really what we're testing there. And then can we count forward? Question 19. Oh, this question has such a little trick halfway through. Let's see if you can spot it. A hall has 1,250 seats. At 7 p.m., so I'm going to do a timeline. This is at 7. 880 seats are filled. Cool. At 8 p.m., there are 40 empty seats. So we've switched it. We've gone from talking about how many seats were filled to now we're talking about how many seats were empty. That's a vital piece of information, else you're going to get trapped. How many seats were filled between 7 and 8? Well, we know 880 were filled at the start, so that's given to us. Thank you. Geez, one thing at least. So we need to figure out how many seats were filled at 8. And then we can do that quite simply. If the hall has 1,250 seats and 40 are empty, we're going to do 1,250, take away the empty seats, which is 40, and we're left with how many seats are filled at 8, which is 1,210. But that's not the end of the question. All we've done now is got the numbers. We can work out the answer. How many seats were filled between 7 and 8? So 880 were filled at 7. 1,210 were filled at 8. We need to know how much of a difference this is here. When we're finding the difference, we're going to subtract 1,210, take away 880, 0 in the ones column, 1 take 8, we're going to have to do some exchanging. 11 take away 8 is 3. 1 take away 8, we're going to have to do some exchanging. 11 take away 8 is still 3. So 330 seats were filled in that hour. Horrible question because look, this just inverts it. Again, lots of people will say, well, it's just problem solving. It would be too simple otherwise. Yeah, I mean, the maths is simple, but hiding it in this way, I don't know, consistently tricky, I must say, as a teacher. That's my opinion. Each day a school has break from 8:15. No, I can't read. From 10:15 to 10:30. Whoops. Lunchtime from 12:40 to 1:30 p.m. That's every day. What is the total time the school takes for breaks and lunch, so combining them, in a 5-day week? So at the end, we're going to have to multiply something by 5 because we're only given the information per day. Let's figure out how much this is in total. 10:15 to 10:30, that's 15 minutes. 12:40 to 1:30, that is 50 minutes. Because if it was 1 hour, it would be until 1:40, so I took 10 minutes off. So in total here, we have 65 minutes multiplied by 5. Hold your horses. You could do this, then you'd have to convert it at the end. What's interesting is you also could write it as 1 hour and 5 minutes first and then multiply it by 5 because you can just partition it. 5 times 1 hour is 5 hours. 5 times 5 minutes is 25 minutes. Okay, you could have done 65 times 5 and you get 325. Then you'd have to just convert 300 into 5 hours and 25 is left over in 25 minutes, known as 60 minutes per hour. That's really important here. However you did this, you should get 5 hours and 25 minutes. There are a lot of questions on this test as well, by the way. We go up to question 27. So some tricky ones coming up now still. Tick all the correct statements. This is all about knowing the difference between parallel and perpendicular. Parallel lines will never ever meet. And you know this because, look, it helps with the spelling. In parallel, in the word parallel, there are parallel lines. I'm going to zoom in and show you. Let's see. Look, can you see here? These two lines are parallel, the two L's. Interesting, right? Let's go back to normal size. So 2 lines are parallel. And then perpendicular means that it makes a right angle. Again, what you should be looking for here is a square. You can see them in here because this square represents 90-degree angle going straight up. So let's take a look at the statements. AB is parallel to CD. So AB is from this point to this point. So it's this line. That's AB. Parallel to CD. C goes to D down here. They are not parallel. That's perpendicular. So I'm not going to do that. I'm not going to tick that. It's incorrect. Let me get rid of those lines. Next one, GH is parallel to AB. GH is this bottom line, and we just did AB was this top line. Absolutely correct. Yes, they are parallel. Give that a tick. Next one, CD is perpendicular to GH. CD, and we know GH because we just talked about it. Absolutely, we can see, look, it's proven by this right angle. Tick. That is perpendicular. Fantastic. And the last one, EF is perpendicular to CD. EF is here. CD is there. They are not perpendicular. They're parallel. Leave it blank. It's just a way to test your knowledge, really, of what those two words mean. Fair question, in my opinion. This table shows the distance that 5 friends travel to school each day. Amina, William, Layla, Chen, and Dev. What is the mean distance they travel to school each day? Again, what is the mean distance they travel to school each day? Quite a simple, straightforward way of just calculating the mean. To do so, we have to add up all of the distances together and then divide by how many distances we added, which was 5 in this case. So I'm going to do the addition here because it's just already lined up for me. 8 plus 2 is 10. 4 plus 6 is 10. So I've got 20 so far. Plus 5 is 25. So I put 5 in this column and exchange over the 2. Putting my decimal in there is really important. When you're adding more than 2 numbers together, you can still add them at the same time. 1 plus 2 is 3. Plus 3 is 6. Plus 1 is 7. Plus 4 is 11. Plus 2 is 13. So we have 13.5 kilometers. That's the first part of our 2-mark question. Once we've got 13.5 kilometers, we're going to divide it by the 5 people we had. 5s into 1 obviously don't go. Exchange over. 5s into 13 go twice. Exchange over the 3 and put the decimal in. Really important. 5s into 35 go 7 times. The answer is 27, right? No! Lots of children might put this and get it wrong because 27, no. You have to put the decimal place in. It's 2.7. Completely different answer otherwise. And you'll notice it doesn't give you any decimals in here. So it's relying on you to write that information down correctly. Mr. Mills has 940 seeds to plant into trays. She plants 12 seeds in each tray. The last tray is not full. Now, quite often, questions would stop here and say, how many seeds were left over? Or how many seeds were in the last tray? And that's a classic remainder question. This is just another example of how this test makes it incredibly hard. What fraction of the last tray was filled? It just gives you another step. And it's still only for 2 marks. And I must say, I thought this was really harsh, guys. I must say. Mrs. Mills, 940 seeds into trays, 12 in each tray. So what we're doing here really is 940 divided by 12. So 12s into 9 obviously don't go. 12s into 94. But if you know your 12 times table, you can jump straight to 60. It's 5 12s. 72 is 6 12s. 84, is 7 12s. So we're going to have 7 12s right here. So 84 gets us 7 12s. How close are we to 94? Well, we're 10 away. So that 10 has to get exchanged over. How many 12s in 100? Again, we already know 7 12s are 84. 8 12s are 96, and that's as close as we can get. So 8 12s are 96. Remainder 4 to get up to 100. So 940 divided by 12 is 78, remainder 4. And now what we need to do, you can't just stop there. We can't just put 4. That's wrong. Because there are 4 seeds left over. That's what that remainder means. But we need to know what fraction of the tray is filled. So in the last tray, she puts those 4 seeds. Out of how many spaces in total? Well, we're told there are 12 seeds in each tray. 4 out of 12. That's the answer. 4 out of 12. And again, they did this in the arithmetic so much. You could try and simplify this to 1 out of 3. Both are correct, but you don't have to. 4 12s is still also correct. 4 12s of that tray is filled. It doesn't say you must simplify. It's just another opportunity at the end to get it wrong because we're adding an extra step in. Oh, the further I get through this paper, the more I think they really were trying to trick people out. Here are 4 numbers, 40, 60, 64, and 100. Use each number once to complete these statements. As always with these questions, there might be numbers here which could go into different, more than one answer, but there's only one way to arrange all 4 correctly. So thinking of a square number, out of these 4, 64 is a square number, but I'm not going to put it as my answer straight away because I also know 100 is a square number. A square number is an answer to a question where you multiply a number by itself. So 64 is 8 squared. 8 times 8 is 64. And 100 is 10 squared. 10 times 10 is 100. So what I'm going to do when there's 2 options is I'm not going to put it in, okay? Because one of these is going to have to go somewhere else. Is a cube number. Again, a cube number, we take a number, we multiply it by itself, and we multiply it by itself again. 1 cubed is 1. 2 cubed is 2 times 2 times 2, which is 8. 3 cubed is 27. 4 cubed is 64. So 64 is a cube number. 4 times 4 times 4. 100 is not a cube number. It doesn't work in that respect. So 64, you can see, if I'd just rushed and put 64 as a square number, I'd have been stuck. So instead, I'm going to put 64 as my cube number, get rid of it. And then that also means, by the way, only 100 can now go into the top. And that's how we work out this question carefully and systematically. Now we want a common multiple of 4 and 5. Which one of these here is in the 4 times table and the 5 times table? Well, you'll never guess what. They both are. 40 is in the 4 times table, obviously in the 5 times table. 60 is in the 4 times table and the 5 times table. Another way to try and trick you. So we have to look at the bottom one. Is a common factor of 80 and 60. So I want a number that goes into 80 and goes into 120, not 60. Only 40 does that because 60 does not go exactly into 80. So now we know it's 40. Again, 40 was the first number you could have jumped in with here and you would have got it wrong because it has to go only once. This is such a nasty layout. You could easily test if we know what square numbers are, cube numbers are, multiples and factors without just building it in a way to basically test using things only once. I don't like that question. That's my personal opinion. 25. Write the missing numbers so that 3 times b minus a equals 2. There was a lot of talk about this question and the formatting again. Okay, you might want to test on algebra, but why is it laid out like this? Anyway, what we're doing is, this row is one question. I don't think that's very clear. They could have separated these out. This row is one question. So what we're going to do is, if b is 2, by the way, b comes first in the question. Again, no need for that. It's just insane. 3 times b, 3 times 2 minus a equals 2. So I'm swapping in the b because now I can work out what a is. So 3 times 2 is 6. 6 minus a equals 2. What do you take away from 6 to get to 2? It's 4. So you put the answer in there. Now we're going to write a new, using this new question rather, using the same formula. We're going to have 3 times b. So again, we don't know b this time. Minus a, which is 13, equals 2. So what I'm going to do, I'm going to add 13 to each side. So we have 3 times b equals 15. Okay, what I did there was I added 13, which cancels out the minus 13, and I added 13 here, which makes 15, if that makes any sense. Again, if you know algebra well, you understand what I just did, but it's just within this question. 3 times b is 15. 3 lots of what is 15? The answer is 5. It's perfectly solvable. Just the way it's laid out again will mean that people who know algebra and how to work out that question will have got it wrong simply because of the formatting. That's when I don't like these questions. Here are 3 translations on a coordinates grid. Tick the translations that are 4 units to the left. There's not even a grid here. This is so abstract. I mean, this is tricky stuff. From 0, 2 to 4, 2. Now, what's interesting to know, 0, 2, so we start at 0, 0. 0 across, 2 up. So we're going to be here to 4, 2. 4 across and 2 up. But that is a move of 4. To go from 0 on the x-axis to 4, that is a shift of 4 units. But it's to the right. It's going from 0 across to 4. From 0 to 4. Horrible trick, because lots of people might work out, yeah, it's 4. Okay, that works. No. Because the next one is actually the answer. From 6, 8 to 2, 8. We're going from 6 on the x-axis to 2. That is a move of 4 across. Okay? So tick the translations that are 4 units to the left. Yes, this works in this case. Now let's check the last one, because it says, by the way, plural, translations, not translation. Minus 3 to minus 7. Think of the x-axis again. If this is 0, minus 3 is here. Minus 7 is there. We're going to go from minus 3 across to minus 7. That is a movement left. So it's the bottom one as well. You had to get both just to get the mark. Second to last question, so it was tricky. And here is the last one right here. Olivia has 2 jars of beads. I think it's the last one. Yes, let's see if we can solve this one. Olivia has 2 jars of beads. The number of beads in jar A is double the number of beads in jar B. Olivia says 25% of the number of beads in jar A is the same as 50% of the number of beads in jar B. Explain why Olivia is correct. Now, one thing you could do here is you could assign amounts of beads to prove it. Okay, so for example, jar A, because we're using percentages, let's say jar A, if it had 100, okay, and that means jar B would have 50 because it's half. We got told that here. A is double jar B, so that means jar B is half of jar A. 25% of beads in A, so 25% of that is 25%, is the same as 50% of jar B, which is half. What's half of 50? Half of 50 is 25. So we could prove it with hypothetical numbers. You could also say that 25% of a number is the same as 50% of half of that. But the point there is you probably wouldn't get the mark. Okay, the reason is because you're just repeating the question. The best way to do it is to prove it. Pick numbers, do maths, and prove it. Okay, and what you've proven here is that 1/4 of a number, of whatever number it is the same as half of a different number that is half of the original one that you just found the quarter of. Very wordy. That's why I always say in these explain questions, pick a number and prove it. Because what you've done there is you've proven it, then all you're simply going to have to do is do an explanation, a simple sentence to say why that's proven it. Okay? So when it says explain, don't be scared of doing some maths to explain it and prove it. What we've done there is picked a random number, because it doesn't matter what the number is, as long as A is double B, it's going to work out. 50% of B is the same as 25% of A. I thought that was a tricky paper. I don't think there were many questions in there that didn't really try and ham up and make a difficult thing for you guys to work out. But I'll be back with paper 3 anyway. Let me know down in the comments what you thought, what you think you would get out of a total marks on this question of 35. Tricky one, and if you thought it was easy, let me know as well down below. Guys, I'll catch you next time. Make sure you like, subscribe, and share this video, and we'll be back for more content as always in the future.